that you see here with okay. So the focus will be on the sinking of fluid into a porous medium, like you see here in this porous packing, sand packing you have here, where I pour water. And as this water is poured, it's sinking into the soil. And as it is sinking into the soil, it makes this mix of the air and water. So you start with an unsaturated soil. If you continue to pour, you create a saturated soil. But most during the phase of the sinking of the water into the soil by the gravitational pull will be a mixture of the air water. And I will focus in this talk on the mixing of and the properties of the mixing of those two fluids and the dispersion of solutes that you have in the fluid. So that will be the key focus of this presentation. So the motivation is on the soil. So if I look at the unsaturated soil, you know, there's what is called the vadose zone, the part of the soil that is above the water table, where the water and air coexist in the pores. It plays an important role in the hydrological cycle, and it regulates both the dispersion and infiltration of the solutes into the soil and how it sinks further down into the water table. So it has an impact on contaminant infiltration and nutrient dispersion, something in farmland, of course, of high relevance. And then what you see on the right is an example of some soil from farmland in a study from Sweden, where they did X-ray tomography of a 10 centimeter column of soil in the surface, and then 10 to 20 centimeters further down where it's compacted. And you see this nice pore structure in this system that then compactifies and become more like a heterogeneous distribution of pathways for the fluid to migrate down into the soil. So the question is, what does this pore structure, what influence does it have on this dispersion when you are not in a fully saturated scenario? So I'll show some movies some of you have seen before, some examples, because I mean the single phase flow, as we know, it is fairly boring from a physics point of view because of the time reversible properties of the fluid flow. So being this little fish larva, this example here, trying to gather some nutrients. Let me try and play this movie again, if I can. Just go back and forward. You see it gets the food into the mouth, it closes the mouth, and the food comes out again. So it's because of the time reversibility of the single phase flow, it comes in and it goes out, as you see. So the opening and closing, there's no difference. Whether you play forward or backward in time, it will have the exact same consequence. So there's no way, without breaking the symmetry, that this little fish larva will be able to feed on the nutrients in the water surrounding it. So it has somehow to break the symmetry. So how do you break the symmetry? Well, you can break the symmetry in many ways. You can go to higher flow rates, and then the symmetry comes through the nonlinear term in the Reynolds equation, or Navier-Stokes equation. In contrast to the Stokes equation you have here. Or you can introduce a second phase, and in the second phase of the flow, you have the surface tension forces between the two fluids, and there's a difference between driving, in this example, a wetting fluid into a non-wetting fluid, where the surface tension forces, there's a difference between the force that you need to apply to driving these two fluids. So that is one example of symmetry breaking. Another is this instability, the Saffman-Taylor instability you create when you drive a less viscous fluid into a more viscous fluid. And then under the surface tension force, you create this viscous pattern. So those are two examples of breaking the symmetry that makes two-phase flow so much more interesting than the single-phase flow. So what are the non-dimensionless numbers that I will focus on in this presentation? So the numbers that I will focus on is the bond number, which is the gravitational pull or the body force pull on the fluid relative to the surface tension force. And then the capillary number is the viscous dissipation relative to the surface forces. And that is, in my presentation, essentially a number of the flow rate. And this is essentially a non-dimensionless number of the forcing that I use to drive this flow in the system. So I will mostly focus, or I will only focus on numerical simulations. So let's just highlight a few more of the properties of the two-phase flow. So in a porous medium, so if we have a little wetting cluster sitting in a porous medium blocking a flow of a non-wetting fluid surrounding this wetting cluster, some forcing is required to mobilize this wetting cluster. So as long as you're below this threshold of mobilizing this wetting cluster, you have essentially no flow in the wetting phase of the fluid. So if you look at the wetting, nothing happens. You need to increase the forcing sufficiently high before you see a mobilization of that fluid phase. And then when you're close to this threshold or gets a little step above, you get into this, what is non-linear relation, non-Darcian relation in the flow properties, that the flow rate scales with a power law scaling with a non-trivial exponent. And then only again at higher forcings where the capillary forces are not relevant, you recover linear scaling like a Darcy law again when you are flowing, or proportionality between the forcing and the flow rate, similar to the Darcy law at higher flow rates. So there's this intermediate range when you go down to a very low forcing and then up to some forcing when the capillary forces are not relevant anymore, where you have a non-trivial relation between the flow rate and the forcing. So how do you see that when you run your simulation? So if we look at the at what I have on the x-axis here is the bond number, and as I decrease the forcing, I see that the variance in the velocity relative to the mean velocity squared, you see that it starts to go up as I go below bond number 1. And a bond number 1 corresponds to when the forcing is proportional or similar to the surface tension force. So when it's below 1, you start to see this increase in the fluctuations. And these fluctuations then have an influence on the microscopic flow properties of the system that is then non-trivial. So if we look at some of the many studies, and pioneered also in Oslo, in the group in Oslo, where they did a lot of experiments some 15 years ago on air glycerol mixtures, and there they saw that it's the opposite plot of what I showed, because I had the capillary number on the y-axis and the forcing on the x-axis. Here, the forcing, the pressure drop across the system is on the y-axis, and you have the flow rate on the x-axis. But what you see here is that it goes with there's no proportionality between the pressure drop that drives the fluid and the flow rate. It goes with the square root in the flow rate, or the pressure drop in the square root of the flow rate. Or I would rather say the flow rate goes like the pressure drop squared, to be in the system more similar to what I will consider for the simulations. So nonlinear relationship down at capillary numbers that are below 0.1 or below 1, where there is this balance. And that has been also seen in other experiments subsequently. Here, it's hard to see that it's below. It's not hard to see that it's below 1, but it's hard to see that it's a power law scaling. But at least it's not a proportionality that you have here in this plot between the pressure drop and the capillary. It's also somewhere around 0.3, I think, is what they measure. 0.45 and 0.3 is the exponent here. Other systems seeing the same behavior of here it's the bond number capillary number. Again, there's a regime here where they have something below 1, and there's a regime here where they now plot the capillary versus the bond, where they see this quadratic relationship again. So now the question that I will also focus on in the discussion of this talk is what happens when you then, now I lower the bond number, and then in some of the studies they go back and recover Darcy flow behavior proportionality again when you have a slow flow rate or a slow driving or low driving force on the system. So what is it that gives this proportionality again? And I will discuss that later on. But what is interesting now with the power law I talked about is this nonlinear relationship. You have an intermediate range here, 0.2 decade, where they try to fit this power law, and then the proportionality up here. So the systems that I use in we've used in our simulations are both a 2D and 3D systems. So this is the setup that I will present. So it's a 2048 by 768 system in the 2D, and 256 by 384 by 256 lattice units in the 3D system. So what does it convert to? Well, if I divide it by the diameter of the beads, which are rigid beads that are put in the system that are non-mobile, and the fluid flows between these beads, then it becomes 128 by 48 in the units of the diameters of those beads that I have in the system. So from a simulation point of view, this is probably a fairly big system. 3D moderate system, but comparable to what people study with 3D systems. So that's 16 by 24 by 16 beads approximately in system size. So the porosity is round to have good connectivity. We have chosen a rather large porosity, so it's close to 50% porosity in the 2D system to have a good flow and good connectivity. In 3D, I think the porosity, I forgot now what it was, but around 30% as I remember it, a fairly porous medium. It's boring running with very low porosity when you do simulations because there's less action, but that also takes away maybe a little less or take away a little bit the relevance of the system. So with that, let me show you here a movie, what happens when I have this 2D system and I consider the flow at a low flow rate with a lower bond number. So, and then a higher one, so approximately a factor 3.5 in difference between the bond numbers. So what you see is that I start with my initial configurations of the two phases, the blue fluid phase being the wetting phase and the green being the non-wetting, and the colors represent the flow velocity. So the more red to yellow it becomes, the more pronounced the flow path is relative to the mean flow. So up in the yellow regime, you're up to more than 50 times larger than the mean flow rate that you see in the system. So now what I want you to notice in the system is the difference in the evolution of the structures as this system starts to evolve. So the higher bond number system evolves in a different way, create different fluid clusters than the low flow rate. So let me just run the movie, and then you can see immediately on the left, you see there's more flashing colors, more intermittent flow paths, more strongly enhanced focusing of the streamlines in the left frame, which is the slow flowing. And I have normalized the flow such that visually the average flow is the same. So I normalized the time such that the visual average flow rate is the same. Of course, on the left, it would be slower than the right otherwise. But you see that the intermittency is much more pronounced. And what you also see is that the green clusters now start to coarsen. They start to get bigger with time. Whereas in the right one, everything seems to be fairly mobilized and not much happens. Okay, let me try and run it again. So you can see very quickly this intermittent structure, a lot of flashes, and then long flow paths going all the way through the system. And then you see that the length scale with in particular, if you watch the green one, it's clear to see that the green clusters are becoming more spatially correlated on longer scale than on the right. So now the fundamental question that we try to address is, does this have an impact on the dispersion? If you put some passive traces into this fluid, can you see that this will impact the way that it disperses in the flow? So this is the main question we try to answer. So here, just an example of the flow paths and the intermittency of these flow paths you don't see in the static one, but it gives you this very highly heterogeneous flow field in the slow flowing regime that you don't see in the faster flow regime. So just a little bit discussion about what has been done primarily in single phase. Not much has been done in multi-phase flows. So in single phase flows, it's known that there's an anomalous dispersion in the single phase flow. And what has been observed is that in the longitudinal dispersion, it's super diffusive, and the transverse dispersion is subdiffusive in scale. What does it mean to be super diffusive and subdiffusive? It's if you measure the spatial variance of passive traces released into this fluid, you will see that in the direction transverse to the flow direction, you have that the variance goes sublinearly with time. Whereas the spatial variance in the longitudinal along the flow direction goes sublinear in time. you see for very short times, you're in the Taylor dispersion regime, there you go quadratically. So it drops away from the Taylor dispersion into something that is more than diffusive on the longer time scale, but less than the Taylor dispersion. Here in this example, they had an exponent of 1.5 in the system, and then subdiffusive in the transverse direction. So that means that in the two-phase regime and in the single-phase regime, you have a less effective dispersion than pure diffusion by having following the flow paths for the passive tracers you inject into this fluid. So you're less effective at vecting or transporting nutrients or contaminants transfers to the flow into this system. And the same behavior observed in simulations. So this is in both of them of simulation in another study here, where this is the diffusive part, and this is the longitudinal that then goes faster than the diffusive part. So this is not the variance, but the standard deviation. So in two-phase, what happens in two-phase? So now let's look at the high flow rates first. Now I have the passive tracer. So what you see here in black is flow paths of a large bundle of particles released into this flow. And you see that along all these flow paths that fairly little transverse dispersion. So here you have the flow direction goes from the bottom to the top here in this flow. And then you see that at high flow rates, there's almost no dispersion transverse to the flow rate. Then when I go to lower flow rates, you immediately see that it fans out, all the particles fans out, and you get a much broader distribution of the particle trajectories. And that I've made even more visible in this little panel where I compare single phase, the blue, to the left panel in the figure, the movie you saw before, which are the yellow particles dispersed in that simulation, and then the red. The red being in the left and the yellow being the right panel in the simulation you saw before. So the higher bond number is in the yellow, and then the lower bond number in the red. And you see that it disperses more transverse when you go into the low flowing, slow flowing regime. So we can even zoom in a little bit more and see what happens. So now we zoom in, and you know that if you are in a single phase flow and a simulation, I should just say here at this stage that the single phase flow simulations are done with periodic boundary conditions. I re-inject at the back symmetrically the particles. And in the single phase, the flow paths will be fully connected. So you just follow a closed loop and nothing will happen. And the particle trajectories, the single paths of the passive tracers will not be intersecting at all, just flow in parallel up through the system with no intersection between them. But now when you look at the two-phase, it starts to look a little bit like diffusion, even though it's non-diffusive particles that I advect here. You see that they start to curl up in funny ways that start to look a bit like a random walk, despite the fact that this is without diffusion in the passive tracers, just fully passive tracers not being dispersed. And this is because of the mobilization and fluctuation in the phase boundaries. You lock down some flow paths, you can even start to move backwards with your particles of the flow direction. And then at some later stage, you mobilize again a certain flow path, and then you start moving forward again. So you have this very intermittent behavior, giving you this funny curled behaviors of the particles. So that has an impact on the mixing. So let's look at the impact of the dispersion or the variance of the displacement of these passive tracers. So again, I have these many passive tracers injected into the system. So now I ask, what happens in the longitudinal? Well, in the longitudinal direction, which is the upper line along the flow direction, you see that I more or less follow the single phase, which is the black one here. So I more or less have the same behavior that I showed you in the simulations before. For the single phase, it goes super diffusively, the dispersion, or super linearly, the dispersion. But then I take the transverse, and I see that the transverse then goes into a linear regime up here. And then therefore goes into a pure diffusive regime, which is very different from what you had in the single phase. But what is more interesting then is that the amplitude of this dispersion goes up, which you could have seen in the movie before, that the amplitude goes up in front of the linear behavior as you go into lower and lower bond numbers. So then the question is, first, can we understand this behavior and get some scaling regime for it? The other is, how far can we then go down to increase this dispersion in the flow rates? Will it continue to all the way down to zero flow, that you just amplify the dispersion such that if you're sitting close to the critical point before you start mobilizing the fluids, you almost have infinite dispersion? So that is the question that we should try to address. So let me just talk a little bit about the dispersion here and the protocols that we followed in our simulations. So we have a mean flow rate that I plot here in the x-axis, but then there are two ways to vary the bond number. So do you remember the bond number was the gravitational pull or the body pull on the fluid relative to the surface tension force, which I call gamma here. So now I can vary either gamma or I can vary the gravity. And then I look at the transverse dispersion, and I see that if I vary gravity slowly with the mean flow, I see that the transverse dispersion goes up when I don't normalize with the mean flow rate. But if I vary the surface tension, you see that as I increase the surface tension, you also have an increase in the dispersion, because many flow paths will be blocked, because when the surface tension is higher, there are certain bottlenecks through the beads that will not be permissible for the fluid to flow through. So you have to find a detour going further around that will increase the dispersion. And at the same time, that also means that the mean flow speed goes down. So now we have these two with the bond number. So this is not a good description. It's not the relevant parameter that we should vary if it depends on these two individually. It's not the bond number itself. So we have somehow to find the scaling function that will collapse these two curves onto one curve, relating the transverse dispersion to some quantity. So let's come up with some arguments and see. So we have an argument very similar to the argument they also had in the papers in Oslo back 15 years ago for what is a stable cluster size or stable cluster size for flow at a certain flow rate that you have in your system. When is this wetting cluster no longer stable and then will break down under the pressure of the driving force of the fluid, and then flow paths will start to form through this cluster. So we just came up with a very simple little statistical mechanical argument, ending up essentially with the same result that they had back in the Oslo papers, but just starting from a more simple or simple statistical consideration here. So in all its simplicity, what is the consideration? We say that there's a critical pressure here to break through between two beads, and there's a length scale. So for that length scale, you can create a capillary pressure, which is the surface tension divided by this length scale. And then there's the critical pressure, so some pressure that you push on this surface. So then we say that, that there's some distribution of these critical pressures for all these gaps between the beads. And we say there's some characteristic pressure, it's not broadly distributed. And then for simplicity, let's assume that this is an exponential distribution. We could also choose any other distribution with a characteristic pressure, but here we chose an exponential. But the argument should work with any distribution with a fixed scale and not a broad distribution in the critical pressures to go through these pore throats. So the pressure jump across the cluster is the size of the cluster. Now we assume aspect ratio 1 to keep things simple, not elongated clusters. So it's the density times the gravity times the length of the cluster. That is the forcing acting on this cluster. So now, what is the probability that the critical pressure is larger than the pull? And if that probability is the probability that is not mobilized, the fluid. So that is just taking this one, integrating up, and because it's an exponential, you also get an exponential out when you integrate this up with the same form here with this delta p, which is the delta p across the clusters. So now you ask if you have n paths along, so we have 1, 2, 3, 4 here on this cluster. I have these 4 entries. So now I ask, how many of these can I maintain before I reach under this distribution a site where the fluid can go through? So that would be this probability to the power n, where n is the size of the cluster and the typical bead size. So that will be n of them. So I ask q to the n, what is that probability? And then I ask, when this one becomes of the order, this lambda becomes of comparable to these terms, I put in the lambda and the L, and so the L comes from so I lift this Q to the lambda L, so I multiply lambda and L in here and eta, and then I insert this lambda rho G in here, and then I get this expression here, the exponential. So now I ask, when does this lambda become comparable to this lambda square becomes comparable to these terms? Because this is where you expect the cluster to become stable or unstable, the transition between them. So when you do that, you say that this lambda should then be proportional to the square root of the surface tension rho G. So for those of you will immediately say, what is this number we just recovered here? Well, that is what is called the capillary length. So that is the length scale of a water droplet you put on a surface. So if you take the capillary length of the surface tension force, it gives you the same scale. But note that here we didn't do the calculation here where you balance the forces like you do when you derive the capillary length. Here we did it from a calculation of a distribution of these floats. So this and the penetration through these floats, we recovered the capillary length. So it's interesting because there's not as such a capillary length in the system because this scale is may or may not be at all comparable to what would be the capillary length in a free droplet on a surface. But nonetheless, this is the scale we get out. So now let me come back to this plot before, because we didn't have the satisfactory description of this in terms of the bond number of the transverse dispersion, because we had these two curves in the bond number that are not collapsing into one curve. But now what if we plot this dispersion divided by this dimensionless, so making it dimensionless, the transverse dispersion divided by the length scale and the average velocity, making it dimensionless, and then plot it versus this capillary length divided also by the characteristic length scale. We see that these two curves collapse into a single curve. So we then have this description of the dispersion in the system. So that was a neat little scaling argument that you could collapse this curve and you can get a better description. So it is not the bond number, but it's the capillary length that is the relevant quantity for describing the dispersion. But does that make sense? Well, it does, because if you come back to the movie I showed you before, as you saw in the slow flowing, you had a larger length scale. And this larger length scale then results in a larger dispersion, because this is the capillary length that becomes larger in the slow flowing regime. And because it becomes larger in the slow flowing regime, you have a larger dispersion. So let's see if it's also what when we try and map the size of the fluid clusters, see if it's consistent with what we see in the simulation for the fluid clusters. So here we try to measure the average width of clusters versus this lambda that we relate to the bond number. So this lambda is related to the bond number. So we just plot the average width of the clusters relative to this 1 over bond number. And we see that this goes proportional to the average size, saying that this lambda is somewhat related to the average width of the clusters with this proportionality. So the length scale goes up when you go into slower flow regimes, and because the length scale goes up, then you have a larger transverse dispersion, because you have to go a larger detour before you can find a flow path through the system. Hope this is clear, this argument. Otherwise, please speak up. So now what we do next is then to try and add a bit of diffusion into this system. There's a question coming.
Yes, Joachim, it's Eric. I don't know if you can see me.
Yeah, I see you. I see you.
Okay, so I was wondering about your width versus lambda plot. It seems like the clusters are wider than they are long. Is that correct, or am I misunderstanding?
Yeah, in this one, in this plot, yes, yes. So this is actually not a good plot that we made, and it didn't end up in the final paper, because this is a bond number 1.18. This is fairly fast, and there the clusters become very elongated. And we are down in the regime of 0.78 that you saw before, where it wasn't that elongated if I come back to the movie before. So the better would be to look at the cluster sizes in this movie that I had here. So if you
they look like they're longer than they're wide. If long means the extension in the flow direction.
yeah, that is true. And as I told you in the beginning, we do this approximation of saying that it's aspect ratio 1, knowing that this is not a complete true argument. So we probably need some, because I also know that in the Oslo papers that you had a plot of the longitudinal length to the transverse length, which is not 1 and it goes up the change in the aspect ratio as you go to faster flows. So it is indeed true, and it's a simplifying assumption, and then we should try and find the correction by putting in if there's a scaling law relation that would then maybe drive it away from this perfect scaling that we have here in this system. So indeed, it is a good point, and we know that it's not a perfect description in that way.
I think we saw the same, that the one length was proportional to the other.
You assume the same. Sorry, I didn't hear you.
I was saying that we did see a proportionality between the longitudinal length and the width.
So I remember you had a scaling relation, right? As I remember.
Well, yeah, in linear.
I forgot, but yeah, we discussed it with Joachim at some point, and then there is yeah. So it is an assumption, and then Gaude is now measuring. Maybe Gaude can tell a little bit. It seems that the aspect ratio is not far off when you are in the slow flowing regime. It seems that they are close to an aspect ratio of 1 in the slower flowing. But when you go to the faster flow, I'm sorry, Gaude, I throw you in for the argument, but maybe you can show your plot you showed this morning at some point to Eirik.
We can discuss it. Yeah. Okay, please go on, Joachim. We have to interrupt you.
So yeah, so when we measure the average width, so this is the width of the clusters, not the height of the clusters that I plot here. And then there's this proportionality. And then with the height, I can do that as well. And I'll probably see a different slope, but with some proportionality, as far as I remember when I did it back when I made this figure. Okay, so now the next step, this is like passive traces, but we want to add a bit of diffusion and see what influence diffusion has. So we also introduce a Peclet number into the system. So we say that we add a bit of molecular diffusion to these passive traces that then moving with different Peclet numbers, and then we see how this transverse dispersion goes relative to this molecular diffusion as we go to higher and higher Peclet numbers, meaning going to lower and lower molecular diffusions. So we see that the difference in the flow rates, if we have these two flow rates, we have an order of magnitude different in the flow rates. It amplifies also, and then as you go slower and slower molecular diffusions, you see that you amplify more broadly the dispersion, the transverse dispersion relative to the molecular diffusion as you go into the slow regime. When you go into the faster flow regime, again, all these curves collapse into a single, that the molecular diffusion and the transverse dispersion is the same. Sorry, this is in the slower flowing or higher molecular diffusion. So what we vary here is the molecular diffusion. So when you go into higher molecular diffusion up here, that it dominates over the advected dispersion from the flow rate, and then they collapse into this single curve. But what I want you to pay attention to here is the right plot, because it shows the capillary number versus the Peclet number. And then as we lower the capillary number, what was interesting is that we saw that as you go lower and lower, you see this increase in the dispersion. So what you have the color, the more yellow the color, the higher dispersion relative to the single phase dispersion. You see an up to a factor 10 increase here at a capillary number 10 to the minus 3 and a Peclet number of around 10. You see approximately a factor 10 increase in the dispersion relative to single phase dispersion. So then the question we were also asked by the referees when we submitted this study is, how far does this extend down? Does it extend down to a relevant regime where you have the capillary numbers you see in soil, for instance? So let me come back to that in a moment. Just let me show again here the same plot. You have the capillary of the wetting, non-wetting, and we have the variance versus the mean velocity. And you see they go up as you decrease the capillary numbers of the wetting, non-wetting. And then we started looking into the literature, what people have done, going even further down to see if they could go see the same fluctuation. So in this study by Gao from the Imperial College, the study they did there, looking at the flow paths, and they had what is called dynamic connectivity, that you mobilize all fluid clusters. And then if they argue that when you go sufficiently far down in the capillary number, at some point you will no longer mobilize all the fluid phases. And you have what is called fixed flow pathways. So our study was more or less limited to this regime in the green box up here. But then they argue as you go further and further down. So the blue crosses here, they call, if you go and look at the blue crosses, they say they are fixed pathways. Nothing is happening. They're not dynamic. So that means that in our argument, when you go down into that regime, in that regime, we would no longer see the enhanced dispersion, because when everything is static, it becomes more essentially like a single phase flow. So we will not have this enhanced dispersion. So we would only see the enhanced dispersion down to a certain value. And that started us speculate, what is the capillary number for that? So they would say the capillary number is around 10 to the minus 5, maybe down to 10 to the minus 6. But when you go down below 10 to the minus 6, you will no longer see the mobilization. You will have single flow paths that are fixed through the system, and then you would not have this enhanced dispersion. So the question is, what is the capillary number in the soil that we have here? I don't know if I should do an estimate. Let me see, would I be able to estimate it? Let's say this is a millimeter a second sinking into the sand. So that would be 10 to the minus 3 times viscosity 10 to the minus 3. So that's 10 to the minus 6 divided by the surface tension. And what is the surface tension? That is around 0.1 fluid air. So that would be 10 to the minus 5 in this case. So I think in this case, the dispersion that we see would still be active. But then as you sink further down into the soil, it's very likely you will recover capillary numbers of 10 to the minus 7 or even below that as the flow gets slower and you sink in close to the water table. So then the argument is, how far down is that the case, and what is it that happens when you have these transient pathways? And then I had a very nice discussion with Alex Hansen when I was up there a couple of months ago in Trondheim, because what you see with this flow is that when you go for a very long time, if I take a simulation, let's take this 2D simulation. So this is a finite element simulation with code from Gaudis. You follow this flow, you see, let me just go back again. So you see you have on the back here, you have an imbibition side and a drainage side. We follow this simulation and we just let it run for a very long time. Then what happens, because of the periodicity of the system and running that, is that you will start to connect flow paths through the system. Already here you have a connecting flow path through, and then the system will evolve for a very, very long time, but eventually it will become stagnant in this low capillary number regime, short circuit, and you would have little mobilization of flow paths. So there's a transient until here. You see now it's much less mobile, and this continues to run for 3 minutes. But since I don't have infinite time, I will not show you all the way. But then eventually it gets stagnant and nothing happens. You have connected flow paths, and there's nothing happening in this regime. I can go to a smaller system, a larger system. Sorry, then it will take even longer. But again, you have the same behavior that in the larger system. Now, as you can see, I show it with the same capillary number, the same system. You see now it takes a lot longer to create these connected paths through. But eventually also that one, for even longer time, if I show you this full movie, will also end up being connected and reaching this state where everything is bonded up with paths through the system. And when you do co-injection experiments, as they do in the experiments, you inject for a long time, and at some point you will also at slow flow regimes reach into a state where you have a fixed flow paths through the system. And then you would also not see this enhanced dispersion. So the question is, I mean, how far down, and that is what we don't have the answer to yet, and what we are really trying to look into, do you really have to go in order to, before you will not have this enhanced dispersion? And would you, as I showed you in this plot, as you go down in this plot, have more and more dispersion as you go down in the capillary number? Or would it just stop at around 10 to the minus 5, and then there would be no more dispersion because all the flow paths become stagnant? And I would say it's like this finite size effect you have in many StatMech systems. Because if I took an even larger system, it would take even longer before I got into the stagnant state. So the question is, what comes first? If I go to an even larger system, can I go then to a lower capillary number, and then I will still see an enhanced dispersion? And then you would say yes, up to a certain point. And then I lower the capillary number, then I would see nothing. But then I would say maybe if you take a larger system, you would still see it as long as you're above the threshold for activating the flow. So here is just an example of the lifetime before you short circuit and you freeze the system. So it seems to go, lifetime seems to go exponential in the system size, which is often what you see also when you do directed percolation simulations. That at some point the system collapses due to finite sizes when it's small, but the lifetime it takes when you're close to the critical point goes exponential when you increase the system size, the stability of the system. And so here an exponential increase in the lifetime. So this is where we are going, and I know that many of you have much better insight into these arguments than me. So I would welcome any input into what is actually coming first. The fact that at a finite low capillary number we would see no more dispersion, or is it because we're just studying finite systems and I could just take a larger system and I will still have lots of activated flow paths? But since the transients become longer and longer, it's not possible to answer that numerically. You probably have to think beyond the numerics to answer that question. So with that, let me just point you towards the paper that was published 4 months ago, for which summarize all the results I presented in this talk. And then I would also advocate for a postdoc position that we have in fluid, if any of you are interested or you know anyone interested in coming to Copenhagen, studying fluid mechanics or computation fluid mechanics. So with that, I would say thank you. So the conclusion, slow, but perhaps not too slow, flow can greatly enhance transverse dispersion. So future studies have to illuminate whether this is relevant in unsaturated soil, except for the example I showed you with sand. But if you go further down in soil, is it relevant in this study? So with that, thank you for your attention.